Good morning, students. In the last session, we have studied about S and P block elements, and now we will continue the session with the classification of elements into D block and F block, followed by the next one. So now D block elements. So with respect to the definition, using differentiating electron, we already defined S block and P block the same way here also, with a difference that in S block elements and P block elements, differentiating electron has entered the outer shell. You remember the definition, elements in which differentiating electron enters into NS sublevel, elements in which differentiating electron enters into NP sublevel are called as NS, S block and P block elements respectively. We studied in the previous class. But when it comes to D block elements, the definition slightly varies. D block elements are the elements in which the differentiating electron enters into N-1 D sublevel. We already studied N corresponds to ultimate shell, N-1 corresponds to penultimate shell, N corresponds to last shell, N-1 corresponds to last but one shell. In that last but one shell, whatever the D sublevel is available, there the differentiating electron enters, or elements in which the differentiating electron enters into D sublevel of penultimate shell. Even in this way also, penultimate shell, like this also we can define D block elements. Now this D block contains how many series of elements? It contains 4 series of elements. D block contains 4 series of elements, namely 3D series, 4D series, 5D series and 6D series. What are 3D series members? Scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Next, 4D series are yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, rhodium, palladium, silver and cadmium. What are 5D series elements? Lanthanum, hafnium, tantalum, tungsten, rhenium, osmium, iridium, platinum, gold and mercury. And when it comes to 6D series elements, they are actinium, rutherfordium, dubnium, seaborgium, Nailsborium, Hussium, Meitnerium, Domstermatium, Rontgenium and Copernicum. So you have to remember these elements at any cost. See, and these are called as 3D series. You know the reason. Here 3 corresponds to differentiating, the 3D corresponds to the sublevel in which differentiating electron enters. Like as per the definition, if you observe the scandium 21 electronic configuration, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 20 is finished. Now 21 means 3d1. See, where the differentiating electron entered D sublevel of penultimate shell. Ultimate shell is 4th shell, penultimate shell is 3rd shell. So like this 3D corresponds to N-1. When 3 is N-1, what is nth shell? 4th shell. When N-1th shell is 3, nth shell is 4. So already we studied in the beginning of a periodic table. In period number indicates their outer shell number. You remember that. Period number indicates their outer shell number. As N-1th shell is 3 means nth shell is 4. Nth shell is 4 means outer shell is 4 means they belongs to 4th period. This 3D series elements belongs to which period? 4th period. The same way 4D series elements, here 4 is N-1, 4 corresponds to N-1, means N value is 5, 5th shell. Their outer shell is 5th shell, so they belongs to 5th period. 4D series elements belongs to 5th period, likewise 5D belongs to 6th period and 6D belongs to 7th period in the long form of periodic table. Next point is their atomic numbers. 3D series elements atomic numbers ranges from 21 to 30. Atomic numbers ranges from 21 to 30. 31 to 36 will be in P block. 37, 38 will be in S block. Here it starts with 39 up to 48. 39 to 48. After 48, 49, 50 and 54 up to that it is in P block. 55, 56 in S block. This is 57. Lanthanum is 57. Immediately what we expect, the next element we expect it to be 58, no? But it starts with 72. What happened? After 57, next is 72. Where are the 14 elements between 57 and 72? Where are those elements? Right? Where are those elements? They were separately written down the periodic table in F block elements. Okay? Because in those elements, differentiating electron enters into F sublevel. Whereas here, we are talking about elements in which differentiating electron enters into D sublevel. You got the difference? That's why 72 to 80, it extends. 86 in P block, 87, 88 in S block, and 89 is actinium, and 90 to 103 will be in, 90 to 103 will be in F block, and here it starts with 104, 105, 6, 7, 8, 9, 10, 11, 112. So in this way, minimum the beginning and ending members, atomic numbers you have to remember. 3D series contains elements from 21 to 30, 4D series 39 to 48, 5D from 57, 72 to 80, 6D contains elements from 89, 104 to 112. And these elements were also named as transition elements. In the sense, like as these elements were felt as responsible for the transition from metallic nature of S block to non-metallic nature of P block. They were expected as responsible for the transition of metallic nature of S block to non-metallic nature of P block. In that sense, earlier these elements were also called as transition elements. And even though zinc, cadmium and mercury do not show the characteristic properties of these transition elements, they are also studied along with these transition elements under the topic D block elements. Next is their general outer electronic configuration. Their general outer electronic configuration is, if you look at this scandium, just here we had written 4s2 3d1, it started at 4s2 3d1, 3d2, 3, 4, 5, 6, 7, 8, 9, 10. So it is, this series is from 4s2 3d1 to 10. 4s2 is quite common. 3d1, 3d2, 3d3, 4, 5, 6, 7, 8, 9, 10. There is an anomaly here. Already we studied in atomic structure. Anomalous electronic configuration. You remember that? So, chromium and copper shows 4s1 3d5 and 4s1 3d10 respectively because of stability, symmetric stability of half filled or completely filled electronic configuration. So, because of that, for those two elements, sometimes 4s possess one electron. So, what's the electronic configuration of 3d series? 4s 1 to 2, 3d 1 to 10. Yes, similarly, for this series also 5s 1 to 2, 4d 1 to 10. This is 6s 1 to 2, 5d 1 to 10, 7s 1 to 2, 6d 1 to 10. So, ultimate shell and penultimate shell are varying. So, we can give their general outer electronic configuration is ns1r to n-1d 1 to 10. ns1 or 2, n-1d 1 to 10. So n corresponds to ultimate shell, n-1 corresponds to penultimate shell in which the differentiating electron is entering. Understood? And due to the presence of unpaired d electrons, these d block elements possess some characteristic properties like color. They show some specific characteristic properties like color, paramagnetic behavior, variable valency. These are the characteristic properties shown only by these d block elements. No other elements in the periodic table shows these properties. These are the specific characteristics of d block elements, which is due to the presence of unpaired d electrons. Color, paramagnetic behavior, variable valency or variable oxidation state. Of course, meaning wise they are different. And catalytic behavior and complex salt formation, etc. Complex salt formation. Like this, they have a set of characteristic properties. This is about D block elements. Once again, what are D block elements? Elements in which differentiating electron enters into n-1 d sublevel or d sublevel of penultimate shell. These are a 4 series, 3D, 4D, 5D, 6D. In this 3, 4, 5, 6 corresponds to penultimate shell. Then obviously their ultimate shells are 4, 5, 6, 7, which means they belongs to the corresponding 4, 5, 6, 7 periods. Means their outer shells are 4th shell, 5th shell, 6th shell, 7th shell. And members of these 4 series are scandium to zinc and yttrium to cadmium and lanthanum to mercury and actinium to copernicum with their corresponding atomic numbers. We have to remember, I explained you already. Next, these elements were also named as transition elements with a feeling like with an assumption like they felt these elements are responsible for the transition of metallic nature of S block to non-metallic nature of P block. And general outer electronic configuration is NS1 or to N-1D 1 to 10. Here this 1 is possible because of anomalous electronic configuration. We have to recap all those things. And due to the presence of unpaired electrons, these transition elements were expected, they show some characteristic properties like color, paramagnetic behavior, variable valency, catalytic behavior, complex salt formation. Complex salt means suppose you take simple salt, sodium chloride. When it is placed in water, that solution responds for sodium ions as well as chloride ions. That is called a simple salt. Double salt means suppose you take a carnallite, KCl, MgCl 2.6H2O. KCl is there, MgCl2 is there, K plus ion responds, Cl minus ion responds, Mg plus 2 ion responds. So that is a double salt. Complex salt means namesake, so many ions will be available, but all will not show their identity. All ions do not retain their identity in aqueous solution. They behave in such a complex manner. That's why such salts in which all ions do not retain their identity were named as complex salts. Understood? Such complex salts were formed by these transition metals. Of course, all D block elements except zinc, cadmium and mercury and copernicum. Except these 4, rest all D block elements were called as transition elements because these all elements are having unpaired d electrons either in their elemental state or in their +2 common oxidation state. But zinc, cadmium and mercury and copernicum do not possess any unpaired d electrons either in elemental state or in their +2 oxidation state. That's why these are called as non-transition elements. But still their properties will be studied along with the other transition elements. Okay. And when it comes to the next classification, that is F block elements. When it comes to the next block, that is F block elements, the definition is elements in which the differentiating electron enters into F sublevel of anti-penultimate shell. Ultimate, penultimate, anti-penultimate. Last shell is ultimate, last but 1 is penultimate, last but 2 is anti-penultimate. N-1, N-2. This is the notation. Now, elements in which the differentiating electron enters into F sublevel of anti-penultimate shell or N-2 F sublevel. N-1, N-2. N-2 F sublevel are called as F block elements. These F block elements are of 2 series, namely 4F series and 5F series. What are the members of 4F series? Cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium and lutetium. Okay, and these atomic numbers are from 58 to 71. 58 to 71. So 14 elements will come. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay. And 5F series are nothing but thorium, it starts from 90, proactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, mendelevium, nobelium and lawrencium. It is from 90 to 103. Okay, at least the beginning and ending elements of this series must be known. Then automatically, if any question is asked, suppose element 67 belongs to which block, you can directly answer. Understood? For that reason. So these are 4f and 5f. Now by this time you might have noticed why this series is called as 4f. From the definition, elements in which a differentiating electron enters into n-2f sublevel. Here elements are an electron, differentiating electron is entering into 4f sublevel. Here 4 corresponds to n-2. Then what is n value? When n-2 is 4, n is 6. So this 4f series belongs to 6th period because their outer shell is 6th. And 5f series belongs to 7th period because their outer shell is 7. So 4f series belongs to 6th period of the periodic table, 5f series belongs to 7th period of the periodic table. And their general outer electronic configuration, if you observe this cerium 58, it's using the Euler's diagram, or if you are aware of the sequence in either way, their outer configuration will be 6s2, 4f0, 5d, 4f1, 5d1, 4f1, 5d1. This will be the configuration for cerium. Okay, so it starts with 4f1. Promethium, cerium, praseodymium. This is praseodymium. Promethium is this one. Promethium, samarium, europium, gadolinium, terbium, dysprosium. This one. Promethium is this one. Okay, praseodymium will be 6s2, ultimate shell, 5d0, 4f3. Experimentally, this was noticed. Like in this way, theoretically we can continue 4f2, 4f3, but practically it was observed in this way. You can see, cross-check the configuration with the one given in the textbook. It is 4f4. So like this, the differentiating electron is entering neither to ultimate nor to penultimate. Neither to ultimate nor in penultimate, but it is entering in anti-penultimate shell and in that f sublevel. That's why this all comes under f block. And as it is entering into 4f sublevel, they are called as 4f series elements. The electronic configuration can be continued. The same way for these actinides, for 5f series elements, the configuration can be given as 7s2, 6d0, 5f1. So 5f, 5f3, 5f4, like that the electronic configuration will continue. That's why this series is called as 4f series and this is called as 5f series. If you observe this as n, this is n-1 and this is n-2. Their general electronic configuration, outer electronic configuration is ns2. ns is always 2. There is no 1 here. But sometimes n-1 the d sublevel will get 1 electron. Like here it has got 1 electron. And in case of gadolinium also, this is 4f4. See, observe with patience. 5d0, 4f5. 6s2, 5d0, 4f6. 6s2, 5d0, 4f7. This is half-filled electronic configuration. F capacity is 14, half-filled is 7. Now gadolinium will get 6s2, 5d0, 4f8. This is what we expect. Yes or no? But as 4f7 is more stable, it shows anomalous electronic configuration as 4f7, 5d1. So sometimes 5d is getting 1 electron. After the first member, 5d is getting 1 electron. Understood? That's why their general outer electronic configuration. And the next one is again 4f9. 6s2, 5d0, 4f9. That's continuous. So ns2 is quite common. n-1d usually 0, in some cases 1 or 2 cases 1 electron, and n-2f is starting from 1 to 14. So this is the general outer electronic configuration of f block elements, and all these are metals only. That's why they are called as inner transition metals, because electron is entering into inner shells, right? Inner transition metals, they are also called as inner transition metals. All are metals, and 5f series are radioactive elements, and mostly they are man-made. Most of them are man-made. Chemistry of actinoids is more complicated. These are called as actinoids and these are called as lanthanoids, because they come after lanthanum. These elements 4f series were also called as lanthanoids. I am writing here, 4f series are all called as, elements are called as lanthanoids, and 5f series elements were called as actinoids. Okay, the chemistry of actinoids is relatively more complicated than the chemistry of lanthanoid elements because of more number of oxidation states possible for actinoids elements. And elements which come after uranium 92, elements which come after uranium 92 are called as a transuranic elements. Okay, these are some points about F block elements. We have one more classification of elements. Classification of elements based on reactivity. Based on reactivity, these elements of the long form of periodic table are again classified into 4 categories, namely, first one is inert gases. Second one is representative elements. Third one is transition elements. And fourth one is inner transition elements. So there are 4 categories with respect to reactivity. What are they? Inert gases, representative elements, transition and inner transition elements. Even though this is not specified in NCERT textbook, we have to go through because for competitive exams this is very important. This classification. Inert gases means elements of zero group. Elements of zero group are called as inert gases. What are they? Helium, neon, argon, krypton, xenon and radon. Why they are called inert gases? They are chemically inert. That's why they are called inert gases. And as they are very rare in atmosphere, they are also called as rare gases. As they are available in air, they are called as aerogens. They are also called as aerogens. And like this, there are so many zero group elements. They are also called as zero group elements because their valency is 0. And all are gases. And all are monoatomic in nature. All these rare gases or inert gases are monoatomic. Means they exist, they are available as helium, He, neon. Single atom is available because they won't combine with anything. Radon is radioactive and is obtained only during radioactive disintegration of radium. And one more point is, what's their general outer electronic configuration? Their general outer electronic configuration is NS2 NP6, except this is called as octet set of configuration, except for helium, which has 1s2 duplet set of configuration. Except helium, rest all have in the outer shell NS2 NP6 octet set of configuration. Helium has 1s2, that is called as duplet set of configuration. And this is about inert gases. When it comes to representative elements, all S and P block elements, except zero group. Already we separated zero group elements, right? Are called as representative elements. Means in the total periodic table, this is S block and these are P block. Except these zero group elements, remaining alkali metals, alkali net metals, boron family, carbon family, nitrogen family, and oxygen family and halogens. So 1, 2, 3, 4, 5, 6, 7 groups. S block and P block, all S and P block elements except zero group were called as representative elements. Why they are called so? As they were more frequently observed in the study of chemistry, they represent the reactivity of these elements. That's why they are called as representative elements, as they are more frequently observed in the study of chemistry. Their general outer electronic configuration is NS122 corresponds to S block and NS2 NP1 to 5, up to 5 only, because 6 again goes to inert gases. NS122 is only for S block. NS2 NP125 is for the rest of the P block elements, is the general outer electronic configuration of representative elements. Another point we have to notice is representative elements includes all strong metals. See, these are all strong metals and all strong non-metals and all metalloids also. So representative elements includes all strong metals, all strong nonmetals, of course all nonmetals also, and all metalloids also. It includes all metalloids also. And when it comes to transition elements, D block elements except the last series zinc, cadmium, mercury and copernicum were called as transition elements. Whatever the properties shown by D block elements, the same properties also will be shown by transition elements. And inner transition elements means even electronic configuration also, ns1 or 2, n-1d, 1 to 10. The same general outer electronic configuration is shown by transition elements, which was also shown by D block. Even though zinc, cadmium, mercury do not possess unpaired d electrons, this copper, silver and gold possess d10. That's why d10 is included in transition elements. When it comes to inner transition elements, the same F block elements were also called as inner transition elements. The properties of F blocks are nothing but can be studied in the form of properties of inner transition elements. Means the electronic configuration is also same. N-2, N-1D 0 R1, N-2F 1 to 14. So this is another classification based on the reactivity of elements. In our next session, we will discuss about the periodicity and variation of these periodic properties across a period and down the means trends of periodic properties. But to start that periodicity in a successful manner, students must be well versed with these two classifications. They should remember each and every element. All elements' names should be on the tips. Okay. So, hope you all get prepared for the next class with the total periodic table and classification based on electronic configuration and classification based on reactivity of elements. Okay. So, let's meet in our next session. Okay.